Is that okay?
Yeah, looks good. Okay, so welcome to the final session of Random. Our first speaker is Ella Sharakansky, which will talk about Chernoff bounds for high-dimensional expanders.
So, hi, I'm Ella Sharakansky, and I present the Chernoff bound for high-dimensional expanders. This is a joint work with Professor Tali Kaufman. So first, let's go over our motivation behind this work. Sorry. As you probably know, expander graphs have countless applications. One useful and essential property of expander graphs is the expander Chernoff bound. Recently, there is a growing interest in high-dimensional expanders. A notable example is a paper by Anari, Liu, Garan, and Vincent, where they use random walks on high-dimensional expanders to solve a major open problem on counting the bases of matroids. So our goal is to generalize the expander Chernoff bound to higher dimensions. The naive generalization doesn't work because in high-dimensional expanders, there are obstructions that don't exist in one-dimensional expanders, and we'll see how to overcome them. Okay, so first, a few definitions. Given a graph G that is weighted, undirected, and connected, we can have a walk on this graph, and this walk has real eigenvalues, and the largest eigenvalue, lambda1, is always 1. We denote lambda G to be the largest eigenvalue in absolute value, except for lambda1. And we say that G is a two-sided lambda spectral expander if lambda G is smaller or equal to lambda. Now, let's say we have a function f, and we want to estimate its expected value, but we don't want to take random samples of f. So instead, we are walking on an expander graph, and we're taking the average of f on this walk. So the expander Chernoff bound says that the probability of the distance between the sampled average of f and the actual average of f to be greater than epsilon decreases exponentially as t increases, where t is the amount of steps or samples. We also have s in the exponent, and because our samples are not independent, s equals 1 minus lambda 2 of g. And we want s to be as close to 1 as possible. Now, our goal is to generalize this bound to higher dimensions. So let's define a few high-dimensional definitions. Pure absolute simplicial complexes are similar to graphs, except here we have vertices, edges, and also sets of more than 2 vertices, like triangles. All of those sets are called faces, and the dimension of a face is its size minus 1. So the dimension of a vertex is 0, for example. Now, a pure absolute simplicial complex is a set of d-dimensional faces and all of their subsets. Our complexes are also equipped with a probability distribution on the d-dimensional faces and induced distributions on k faces. So an important definition is the link of a face, which is basically its local view. Given a face tau, the link of tau is another complex obtained by taking all of the faces that contain tau and removing the vertices of tau from each one of them. Another definition is the underlying graph of a complex, which is just its vertices and edges. Now we can define high-dimensional expanders. So given a pure absolute simplicial complex, it is a gamma local spectral expander if for every face tau, the underlying graph of the link of tau is a gamma spectral expander. Now, when thinking about the Chernoff bound for expanded graphs, it's actually not a bound for graphs. It's a bound for walks on graphs. So in the high-dimensional setting, we first need to decide which walk we're studying. And the walk we're studying is the lazy upper random walk because it's very related to the structure of the complex. This walk is denoted mk+, and it walks from one k face to another k face through a k+1 face that contains both of them. Now, basically, we can just apply the existing expander Chernoff bound to this high-order random walk mk+ to get a high-dimensional expander Chernoff bound. And this is the bound we get, as before, and now s equals 1 minus lambda 2 of mk+. However, lambda 2 of mk+ is approximately k+1 over k+2, which approaches 1 as k increases. It means that even when the complex is a very good expander, still this bound is bad because S is close to 0. This is why it's called the naive high-dimensional expander Chernoff bound, because it doesn't capture the expansion of the complex. And the reason behind this, as we mentioned earlier, is that in high-dimensional expanders, there are obstructions, and they make some of the eigenvalues of MK plus large. So our idea to overcome this is that if f is a good function, not an obstruction, it shouldn't pay for the complex having obstructions. So we want to find the requirement about f with relation to the complex and its links that implies a Chernoff bound where s equals 1 minus some other eigenvalue of mk plus depending on f. So we define the level of a function. Given a function on k faces, it is from level j plus 1 if its expectation on the links of j faces is 0. And note that this is a combinatorial requirement about f with relation to the complex and its links. Now a quick example, f is from level 0 if its expectation is 0. So we prove this main theorem, the high-dimensional expander Chernoff bound. Given a gamma local spectral expander, assume that gamma is small enough, and we have our function f on the k faces, and assume that the variance of f is small, then if f is from level j plus 1, we have our Chernoff bound where s equals 1 minus k minus j over k plus 2, plus a small value depending on gamma squared. So if f is from a high level, like level k, then s is very close to 1 as long as the complex is a good expander. Now, some of the methods we use to prove this theorem are martingales and a Zoomer's inequality, which is like a Chernoff bound for martingales, and the compositions of ckx, where ckx is the space of functions on k faces. Now, this method of decomposing ckx is actually a useful method for studying high-dimensional expanders in general, and we prove another theorem about 3 well-known decompositions of ckx. So we prove that when gamma is small enough, the following 3 decompositions are equal. The almost orthogonal decomposition by Dickstein, Dinur, Filmus, and Harsha, the combinatorial orthogonal decomposition by Kaufman and Oppenheim, and the spectral orthogonal decomposition by Kaufman and Oppenheim. And as a corollary, when gamma is small enough, the DDFH decomposition is orthogonal. Thank you.
Thank you, Ella. We have time for a couple of questions. If you want to ask a question, please unmute yourself and ask. In the meantime, maybe I'll ask a question. So I might have missed the point. So are you sort of going from the Jth level to the Kth level? Is this the idea or
what do you mean by, is this the idea?
So you said that there is an abstraction for if you go from k to k plus 1, then you are not mixing fast enough.
No, we are not doing the longer walk. We are doing the usual walk, but we are looking at good functions that are associated with smaller eigenvalues of this walk, and these are the functions from here, functions from level j plus 1. So we show in the paper that these are exactly functions that are associated with the smaller eigenvalues of mk plus, which is just the 1 step up and 1 step down walk.
Okay. Okay, thank you.
Can I ask one question just to refine my understanding? So should we view this as a function-dependent Chernoff bound?
Yes, we actually prove a one-dimensional Chernoff bound, like a standard expander Chernoff bound for functions that shrink well, like functions that are associated with these small eigenvalues. So in the longer talk, I show this bound where instead of lambda 2 of mk plus, we have lambda of f that we define.
I see. Okay, thank you.
You're welcome. Thank you.
All right, thank you very much. Maybe it's time to go to the next speaker. So next we have Calvin Bideman from UIUC. Kevin, can you share your slides?
Cool. Everyone see and hear me? So today I'm going to be talking about multi-criteria cuts and size-constrained K-cuts and hypergraphs. This is joint work with Karthikeyan Chandrasekaran and Chao Xu. But actually, I'm going to be focusing on graphs for simplicity in this talk. So I want to start by defining the single criteria min-cut problem. We're given a graph with positive costs on the edges. And for any S subset of the vertices of the graph, we define the cut induced by S, written delta S, as the set of all edges with one endpoint in S and one endpoint in V minus S. And our goal is to find a cut with minimum total cost on the edges. For example, the red edges in the picture. And some classic questions are, given a graph, can we find a min-cut efficiently? And how many min-cuts can an n-vertex graph have? Now, how do we generalize this to multiple criteria? Well, now we're given a graph, and each edge has t different positive costs associated with it, given by function C1 through CT. And there's several different ways to measure the quality of a cut in this setting, so I'm going to define a few. First is parametric min-cuts. We say a cut is a parametric min-cut if it's a single criteria min-cut for some linear combination of the t cost functions. So for example, the red edges here minimize C1 plus half of C2. So it's a parametric min-cut. Next, Pareto optimal cuts. We say that one cut dominates another if it's at least as cheap under every cost function and strictly cheaper under at least one of them. So, and a cut that's not dominated by any other is Pareto optimal. So the red edges here have a total cost of 5, 5. Every other cut has a cost of at least 6 in one of the two cost functions. So this cut is Pareto optimal. Note that it's not parametric, however. Then in the B multi-objective min-cut problem, we're given not only a graph, but also a budget vector B of t-1 budgets. We say that a cut satisfies the ith budget if its CI cost is at most BI. And our goal is to find a cut with minimum CT cost among those that satisfy all t-1 budgets. So for example, in the 2 criteria case, if we're given a budget B1 of 9, we want to find a cut whose C1 cost is at most 9 and whose C2 cost is as small as possible, subject to that constraint. So the red edges are an example. Note that this is not a Pareto optimal cut. And then finally, we find the multi-objective min-cut problem. We're not given a budget vector, and we want to find a cut that's a B multi-objective min-cut for any B. It turns out that every parametric min-cut is Pareto optimal, and every Pareto optimal cut is a multi-objective min-cut. And we can easily find a parametric min-cut by just choosing arbitrary weights and running a regular min-cut algorithm. So this means that we can efficiently find any of these 3 types of cuts. So the only interesting find a cut question is, can we find a B multi-objective min-cut given a specific B? But the structural question, is the number of multi-objective min-cuts in a graph polynomial, is interesting. And note that an affirmative response to this question would imply that the number of Pareto optimal and parametric min-cuts is also polynomial. Also, if the number is polynomial, we can ask if it's possible to enumerate all of them in polynomial time. And our paper answers all 3 of these questions in the affirmative. So let's talk about prior work. In the min-cut problem, it's been shown that the number of min-cuts in a graph or even a hypergraph is O of n squared. And this is tight because the cycle has omega n squared min-cuts. In the multi-criteria case, Karger showed an upper bound of n to the t plus 1 and a lower bound of n to the t over 2 on the number of parametric min-cuts. I see Majab, McCormick, and Queiron showed upper bound of n to the 5th on the number of Pareto optimal cuts for the special case of 2 criteria. And I see Majab and Ravi showed an upper bound of n to the 2t on the number of B multi-objective min-cuts for a fixed B. Our key contribution is an upper bound of n to the 3t minus 1 on the number of multi-objective min-cuts. This implies a matching bound on the number of Pareto optimal cuts, and note that this bound is equal to the bound of IC et al. For the case of t equals 2, and to the tight n squared bound for the case of t equals 1. We also give a lower bound of n to the t on Pareto optimal and multi-objective min-cuts. I want to very briefly talk about our techniques. So we give a random contraction algorithm for the B multi-objective min-cut problem, where we're given a budget with a success probability of 1 over n to the 2t. This is inspired by work of IC et al. Then we know that we can actually move the randomness in this algorithm up front and pick t random orderings of the edges based on the t cost functions, and then only use the budgets to decide which ordering to contract from next. And that means that we can get an algorithm that just tries all possible ways of interleaving and outputs all of the different cuts that it can obtain by interleaving its randomly chosen permutations. And this will output anything the first algorithm could for any choice of B. So using an argument from Karger, we show that the number of interleavings generating distinct cuts is O of n to the t minus 1. And therefore, we have an algorithm for multi-objective min-cut that outputs n to the t minus 1 cuts with a 1 over n to the 2t success probability. And therefore, the number of multi-objective min-cuts is n to the 3t minus 1. Our results also generalize to constant rank hypergraphs using a more complicated LP-based analysis, and also to node budgeted variations of the problem. We also give an algorithm for the size constrained k-cut problem, where we want to find a k-cut given lower bounds on the size of the parts of a partition. And in conclusion, we can solve B multi-objective min-cut efficiently using random contraction. This algorithm with an interleaving argument shows that the number of multi-objective min-cuts is strongly polynomial. This can be extended to constant rank hypergraphs, and random contraction and interleaving can address a variety of other problems. Some open questions are, can the gap between our upper and lower bound be improved? And does any of this generalize to arbitrary rank hypergraphs, where we can't use uniform contraction and therefore our arguments don't extend? So is the number of multi-objective or even parametric min-cuts polynomial? And can we solve B multi-objective min-cut efficiently? Thank you.
Thank you, Kelvin. As before, if you have a question, please unmute yourself and ask. We have time for a quick question. All right, so if there are no further questions, maybe we can move to the next speaker, Lin Tran.
Hi.
Hey.
So I'm going to share the screen. Are you seeing my screen?
Yes, thank you.
Great. So I'm Lin, and I'm going to talk about my work with Professor Van Vu from Yale University, reaching consensus on random networks, the power of Q. So we begin with an election with 2 parties. It's a sort of a hot topic recently. And we assume that the people are influenced by their friends. And we want to know how many voters that we want to bribe to win this election unanimously. So note that we don't need to bribe everyone. The people we bribe will spread our influence from their friends. So we want to bribe only a few people. So let's do this on a graph. We have a graph with n nodes, and initially every node is either red or blue, and on each day the node will look at the colors of its neighbors and change to the color of the majority. But if there's a tie, then it will keep its color. So a color wins if at some point everyone changed to that color. So we want to do this on a GNP random graph. So it's clear that if we start with n2 members on both sides, then they win with the same probability. But what if we give red an advantage of C, so it has n2 plus C members in the beginning? It's easy to prove that in the case that C is linear, then red wins within only one day with probability tending to 1. So we have to reduce this advantage to be meaningful, and we reduce it to a constant. So it turns out that when the constant is big enough, then we can guarantee any probability that red wins, no matter how high it is. So it's the same as saying that we can bribe a constant number of people to win this election, no matter how many people we have in the community.
Sorry,
So
is this independent of P?
Yes, this constant will be dependent on P. So we can see that a very few people will have a huge power over the election. So we call this the power field phenomenon.
Okay.
And to demonstrate this, we have the first theorem. When P equals to 1/2, we only need to bribe 6 people for red to win with probability at least 90%. And it only needs 4 days to win. And for general P and C, where P is a constant, the chance that red wins will be bounded from 1 by a function of P times the maximum of 1 over n, 1 over C squared. So both of these theorems come from our general theorem, the one that we actually proved in our paper. It also describes the process day by day. And for each day, we have a probability that it will occur. So on the first day, the advantage from C will grow to a root n advantage. On the second day, it will be a linear advantage. On the third day, it will be overwhelming. So we have less than half of the expected degree number of blue nodes remaining. And on the fourth day, red win. And we can see that from this, the main term of the probability is the one on the first day. So once red has achieved an advantage of root n on the first day, then we can say that almost surely it will win in the next 3 days. So that's the main theorem, and the precise statement, the proof, will be in our paper.
Lynn, I have a clarification question. So am I assuming that everyone that is not bribed is voting at random? It's like a random initial value? Is this
so they have an opinion initially, and the opinions will stand for the candidates that they're going to vote for, and they will change the opinion on each day.
Right,
and
but the initial opinion is completely random, except for these parties that are.
We can fix them or make them random, as long as we fix the number of people holding each opinion initially.
Mm-hmm.
So you can either like just fix the people that have each opinion, or you can choose the set of red people randomly from all the set with n2 plus C members. They're going to be the same because we are dealing with GNP random graph. So it's not important if we choose the people or just fix them beforehand. So we talk about this in our paper as well.
Okay, thank you.
Yeah, so the techniques that we did for this theorem actually does work when p tends to 0 as a function of n. So it only works for dense random graph. Because we have to tailor the advantage the techniques to get to a very small number. So we sort of highlight that we only need to bribe very few number of people. But for sparse random graphs, we also have a similar theorem. So here we also have the same results, and it works for any p that is larger than 2 plus epsilon times log n over n. And it works whenever the advantage times p is a large constant. And it will be in our next paper. So before ending, I'll talk about some interesting questions. The first one is, we've seen that for the advantage being 0, then the chance that red wins will be close to 1/2. So we conjecture that with only one person as an advantage, then the red will be able to win with probability bounded away from 1/2. So we did an experiment with 10,000 nodes, and we repeat the process 10,000 times, and it shows that the frequency that red wins is more than 93%. So it's surprising, and even more surprising is that red only needs 3 days to win, while we proved it for 4 days. So the proof is still open. Another conjecture is the values of defectors. So we define the value of one defector from blue to red to be the chance that red wins with him, and minus the chance that red wins without him. So you can see that the last defector doesn't add any value because we already have a red win before that. So we conjecture that the values will decrease with the number of defectors. And if this is true, then the previous conjecture is also true, although with a smaller probability compared to the one that we got from the simulation. There are also a bunch of interesting questions we can ask. Like we can try to upper bound the chance that red wins instead of lower bound, or we can try to improve the number 2 in the theorem for sparse graph to 1. So it sort of works whenever the graph is connected, and this is also the best we can do. We can try to increase number of colors, or we can change the updating rules. You can see a survey in 2017 that has a lot of alternative models for this. You can also change the graph to be a preferential attachment graph, so it gets closer to real-life social networks. Thanks for listening.
Thank you. Very interesting phenomena. So are there any questions? Please unmute yourself.
I have one question. So you're choosing C, the extra people, to be sort of arbitrary, independent of the graph. Do you think you can prove conjecture 1 easily if you allow the extra person to just, like you get to see the graph first and then you get to pick the best person?
Well, yeah, so that's another question that we're thinking about. So actually, when we first did this, another colleague of mine told me that probably it's possible to select a special person to try to win the election more easily. But so the first thing that we tried was to pick the person with the most number of neighbors, so that he sort of get a lot of influence. But it turns out that it doesn't increase the chance that red wins by any significant number. So the guess is that if we choose the person this way, he will also be influenced by his neighbors. So there's a chance that the person we pride will turn to the other side on the next day, and it doesn't bring a lot of advantage this way. But maybe it's possible to pick such a person, and we'll think about it.
Cool, thank you.
What about the variant where you draw the graph first and then you can pick, initial members that have the the opinion. Is it clear that there n over 2 is cannot be beaten? I mean,
yeah. So actually, I think this is the same issue as the question that Cyrus asked. So, I mean, here we sort of proves that we can pick the people from outside randomly, provided that the graph is also random. So we don't need to think about which people to pick, and we still got the very high probability to win. But yeah, on theory, it's certainly possible to pick a set of people in order for us to win, but it needs to be sort of close to half of the community, because we actually proved in our paper that when the number of people on the blue side is less than half of the community minus root of n, some factor of root of n, then no matter what the graph is, we will always have a red win. So you don't actually want to pick less than half of the community by a lot.
mm-hmm. Okay, thank you. I think we need to move to the next speaker. Yeah, but yeah, thank you for answering questions. So next is Cyrus Crosschain. He's going to talk about matrix vector queries.
Cool. Hey everyone. So yeah, so I want to talk briefly about these queries, and this is.
So Cyrus, I think we see the this presenter view. So
the wrong thing.
Yeah.
Let's see if I can fix that. Maybe. Yeah, you don't need to see the presenter view. Sorry. Anyway, while I'm setting this up, this is joint work with David Woodruff and Hanlin Zhu. Okay, this should work now. Cool. Okay, so it's a really kind of a simple query model, and I'm a pretty chatty person, so I'd love if people ask me questions about it. And this is kind of a short summary. The other thing is that I spent quite a bit of time making an animated video for this talk, and it's cute, and the things bounce around and stuff. And so if anyone wants to watch it, it's probably going to be much more engaging than what I have to say now. But you can listen to me now first. Okay, so what is this query model? So basically, you get to query a matrix. So this is some unknown matrix M. And the way to query it is you get to choose two vectors U and V, and you just get U transpose MV. And so there's some fixed field, and say this is F2 or the reals or whatever. But you can make these queries, and then you want to do this a bunch of times, as usual, adaptively, randomly, etc. And so you make a bunch of queries, and you want to learn something about the matrix. And so it's kind of a neat model. So like one thing you can do, for example, is that you can simulate a whole bunch of graph queries in this model. So here, this is the adjacency matrix for the 5 cycle. And if you get an indicator vector for one vector and the all ones vector for the other, then you get the row. The row is just the degree. So you can query like edges, degrees. You can find random edges. You can find random neighbors, specific neighbors, cuts, etc. There's like a really large amount of related work. And so I'm actually not going to mention any specific references here just because there's too many of them, and maybe it's more fair to make everyone a little unhappy. Anyway, there's tons of related work. And the reason I like this model is I think we seem to be the first to sort of study it in this generality. And somehow it seems like it captures, for a lot of problems, the main complexity and challenges, even though you get a lot more power. And so in the paper, we have like 18 results or something. It's like a really, really long exploratory paper. Let me mention 3 that kind of highlight the main ideas. So the first is diagonal matrices. So a diagonal matrix is something where all the non-zeros are on the diagonal. This is not a diagonal matrix. And so it turns out we can do this with a constant number of queries, and it's a pretty simple algorithm, and this works over any field. So I think that kind of shows that somehow these queries are pretty powerful. They're global. Maybe you can do something with the whole matrix as opposed to accessing little single entries at a time. We also look at permutation matrices, and here the story gets more interesting. So a permutation matrix, remember, has a single 1 in each row and column. And this is not a permutation because there's like, 2 1s here. And so for this, I'm thinking of binary matrices, and we show an algorithm with a constant number of queries if the queries are over the reals or any large enough fields, but then over F2. So if you only get parities, then we prove a lower bound showing that you need about n queries to determine if it's a permutation or not. And so that's kind of a case where the field matters a lot. And then finally, and this is a result that is much more technical than I can get into in like 1 minute, but it's probably the result that maybe has the most chance of being useful other places. So we look at the Schotten p-norm, which is a matrix norm. That's not really important, but the point is that we find a reduction method in a certain case where you can like simulate these queries with entry-wise queries, assuming your matrix is random in a certain sense. So if it's random and sort of rotationally invariant is what we call it, but basically you can permute the rows I'll show you that in a second. But basically, there's a certain type of random matrix, which is very useful for studying these things because it preserves the singular values. But we can simulate the queries with much more limited queries, and the query blowup is only quadratic. So I think that's pretty neat, and that's the kind of thing that I feel like could be really powerful for other connections to other problems. Okay, so again, everyone, you can stop me or let me continue. I'll say a couple words about each of these things and then mention a little bit of open questions. So here's the diagonal matrix algorithm in brief. And so here, we want to diagonal matrices, test if it's diagonal with a constant number of queries. So we're going to choose random vectors with the constraint that the diagonal is always 0. So choose them so that ui, vi is 0, and then the other entries can just be random. And that's fine. And the point is that if you do it like this and they're random, then you're going to hit a large amount of the matrix. And as long as there's some non-diagonal entry that's truly in the matrix, you're going to hit that. And then it's just sort of short zipple to see that the sum of all these entries, because you sort of have random coefficients of this linear sum, it's going to be non-zero with some constant probability. And so we just run the sort of query algorithm a bunch of times. And if we ever see non-zero, then it's definitely not diagonal. If we see if it's 0, then it's probably diagonal because we don't ever touch the diagonal entries. I think that's like a neat little algorithm. It'd be like fun to teach, for example. And then here's the thing that I said that I think is probably the most technically challenging and potentially important. So here we look at these rotationally invariant distributions where capital U and capital V are random, and you can permute the rows, and they're still the same distribution, and then you have some singular values. And so if these are orthonormal, then it doesn't really change the singular values, it just changes what the singular vectors are. And so this was used previously to prove some lower bounds for estimating the Schotten p-norm. And we show that if you have S queries in the UMV model, then you can have S squared queries in the entry-wise model. You get the same thing. And the proof is not actually too hard. It's just by induction, and say you can simulate the S-1 first queries, and you look at that the last one, and then you just have to kind of show that you can write this in terms of these plus some new queries. And in fact, what we do is we just show that you can just look at the top corner of S squared queries, entry-wise queries, and you can get the exact same distribution as if you had some arbitrary UMV queries. So I think that's pretty neat and kind of, definitely surprising. Like entry-wise queries are very specific. So, okay, and so sort of, wrapping up. Very short talk. So basically, we do a bunch of stuff. There's a bunch of algorithms. It's an exploratory paper. There's a lot of open questions. I would love if people worked on this. I think there's like a bunch of work on triangle estimation. That could be easy in this model. Some people asked about detecting if a matrix is PSD. I think that's going to be hard in general, but maybe if you have eigenvalue gaps, general techniques would be cool. And then personally, I like always blowing things up to higher dimensions. And so maybe you can say, what if we have a k-linear form and you get to specify k query vectors and you get the answer. Anyway, so that's all. Feel free to email me or contact me or ask me questions now. Happy to chat.
Thank you, Cyrus. And I want to say that the videos that you recorded is very professional, so I recommend people watching it.
Thank you.
So do we have questions from the audience? Please unmute yourself and ask a question. In the meantime, maybe I'll ask a question. So you mentioned this S to S squared blow up. Do you think it's necessary?
Yeah, probably. I mean, like the way that proof works is that we kind of express this as these, but then you kind of need enough new entries to make it linearly, not in the like linearly independent, but like probabilistically independent to kind of get the same distribution. So at least our proof feels very tight. Maybe with a slight restriction on the distribution, it's not necessary. And maybe I'm just wrong. Maybe it's not. I hadn't really considered that. It's a nice. I'd have to double check though. It might violate some upper bounds if it's not true, because we use this to get a lower bound.
Mm-hmm. Okay. Very nice. So I guess since we are a little bit behind schedule, maybe we should move to the next talk. So now we'll have Ali Purmiri from Sydney give the next talk about balanced allocation on dynamic hypergraphs. Ali, you can share your slides. Okay. Good, thank you.
Hello, everyone. Welcome to my talk. In this presentation, I'm going to talk about balance allocation in dynamic hypergraph. This is a joint work with Catherine Greenhill and Bernard Mans. Let us first define our setting. We are given a set of n beans and n sequential balls, and our goal is to allocate n balls into n beans so that maximum number of balls at any beans is minimized, which is called the maximum load. The balls into model is are quite general, and they have been seen in many places, such as random graph process, hashing, the randomization hashing function, and load balancing in distributed network. A very simple and intuitive mechanism is called a one-choice process, where each ball picks a random bean uniformly at random, and then the ball is allocated to that bean. It is proved that using this mechanism, the maximum load is at most log n over log n plus some constant. Sorry. Other brother Carlin and Opfall introduced the balance allocation known as power of D choice, in which every ball chooses D beans uniformly at random, and then the ball look at their load information and goes to one with minimum load. And if there is any ties are broken randomly. They showed that after allocating n balls, the maximum load is log plus some constant. Surprisingly, we see that when we increase the number of choices by at least one, the maximum load exponentially decreased to log from a log n in one choice process. The original balance allocation idea is based on the fact that each ball picks D beans independently and uniformly at random. However, in many applications, choosing any random set of D beans is not possible or very costly. For instance, consider a set of servers that are interconnected by a network, and assume that a random request arrives at some node at some region of the network. And in order to minimize the communication cost, it is important that request is satisfied by nearby servers. So it would be very applicable to consider these types of balance allocation, where the some underlying structure are assumed, and hence a dependency among the beans exists. Therefore, it might be impossible to directly apply the original balance allocation in such a setting. Motivated by this application, several variation of balance allocation model has been studied. For instance, the balls into beans with, via local search, where a ball picks a random bean and then the ball is only allowed to search in a local area to find a bean with minimum local load. One of the first results in this area, I mean the balls into beans with a structure, is called balance allocation on graph, introduced by Kentabadi and Pareto. Here they assume that the beans or servers are interconnected as a graph, and then when the ball arrives, pick a random edge from the graph and then look at the beans incident to the graph, and then look at the beans with minimum load, and then ball is allocated to that bean. Here we see a strong correlation between the beans, and then they prove that if the graph is enough dense, then still we got the effect of power of two choices. So they have like 2 log n load here. The second main result is about the balance allocation on hypergraphs. In this result, they assume that there is a hypergraph underlying structure for the beans, and every time over the time a hypergraph exposed to the system, and then the ball picks a random hyper edge from the hypergraph, and then the ball is allocated to one of the beans with minimum load, actually beans within the hyper edge. For example, here to see an example of the hypergraph, here assume that we have n beans that are organized as an n cycle, and each hyper edge here is a path of length log n. And we have a sequential balls, then balls come and choose a path of length log n uniformly at random, and then ball goes to one of them with one of the bean with minimum load. So far we observed that we have 2 main results about the balls into bean with a structure. The first one is defined as the balance allocation on graphs by Kentabadi and Pareto, and they prove that if we are given a dense graph, we can pick 2 choices from the graph, and so the number of choices is 2, and they got the effect of power of 2 choices, and the maximum load is a log n. And the another work is by Godfrey that says that there is a hypergraph underlying structure, and the ball choose a hyper edge from the hypergraph, and here the number of choices is at least log n. So they got the maximum load of a constant. So somehow it's a constant. It's a consistent with the result by Azar and et al. And here we want to close the gap between two previously studied model. So here we want to extend the number of choices to any d between 2 and log n. So here is our model. We consider a dynamic hypergraph, which means that we have an underlying hypergraph structure for the beans, and the hypergraph exposed to the system over time. In fact, we defined dynamic hypergraph as a sequence of hypergraphs with the same ground set, but the age may change over time. We denote the hypergraph with h1 to hn. Then, for example, assume at time t, the hypergraph ht exposed to the system, then a ball comes and choose a random edge from the hypergraph. Then, so the hypergraph should have at least log n beans inside every edge. Then the ball come and choose the random beans from the edge, and then the ball allocated to one of the beans with minimum load. So let us review our model. So we are given a dynamic hypergraph from H1 to H1, arriving over time, and then we fix some D, which can be between 2 and log n. Then at time t, a ball arrives and ball picks a random edge from the ht exposed to the system at time t, and then again D beans from the random edge chosen. Then the ball is allocated to one of them with minimum load. Comparing with the original balance allocation, we can see that we need much less source of the randomness because the beans are chosen from a smaller set of the beans, which is a random edge from the hypergraph. So the main question is that under which condition the algorithm gets the effect of power of D choices. So the very important condition is the visibility. So visibility is that if we are given a dynamic hypergraph, S uniform hypergraph, then for every pair of nodes, a visibility of ij is the number of times that ij appears in a single hyper edge in the hypergraph. So we show that if the dynamic hypergraph is a epsilon visible, then and it's at most s times n to the 1 minus epsilon, then we can get the effect of power of t choices. The second condition that the hypergraph should satisfy is called the balanceness, which means that if our hypergraph is S uniform, then for every bean probability that the bean is chosen by the T's ball is bounded by beta times S over n, where beta is some constant. The last condition is that for given S uniform hypergraph, S should be at least as high as log n. However, in our model, depending on D, we can define other size for the S. For example, we could, even if D is small, S can be some constant.
Okay, so one minute.
Yes. Yes.
Just want to say that if you could try to wrap up in 1 minute.
Okay, sure. And here we see that if hypergraph are satisfied the balanceness, epsilon visibility, and the size condition, then we can see that our dynamic graph also satisfy the 1, 2, 3. These three conditions, then the algorithm also get the maximum load at most log D log n with high probability. Additionally, we show that the condition of 1 and 2 are necessary, otherwise we cannot get the maximum load of log D log n. Yes. Also, we can prove that if we are given a dynamic graph like G1, G2 to the Gn, and they are satisfied the feasibility condition, again, we can get the maximum of the log 2 log n with high probability. Yes. Thanks for your attention. If you have any question, you could ask me now or send me an email.
Thank you, Ali. So please, if you have any questions, please unmute yourself and ask. Feel free to ask. Mm-hmm. All right, so it seems that there aren't any questions. So let's wrap up. I would like to thank all the speakers in this session and all the speakers in the entire conference. This wraps up Random 2020. It was very nice to see you all, and I hope to see you next year as well. So stay safe and bye-bye. Right. I would leave the room open if you want to ask some informal question for a few minutes. So feel free.